Hello, and welcome to this lesson video where we'll get to know how to perform some fundamental quantity calculations for earthwork operations. Specifically, we'll learn about the calculating the quantities for the following earthwork items: structural excavation, site utilities, soil spoils, and cut fill volumes for mass excavation projects. First, pit excavation is performed to remove the soil to reach the specified level for constructing the foundation of a building or other similar structures. We'll see how to calculate the excavation quantities for both small and large pits. As in the shown formula, the excavation volume equals the horizontal area of the pit multiplied by the average excavation depth. The shown depth is on the excavation pit with horizontal dimension of 9.15 meters and 7.63 meters. You can see the excavation depth is at the corners are provided, which were calculated as the difference between the existing and the new grades. So you will need to calculate the average depth as shown, which turns out to be 2.1 meters. Then the area is calculated to be 72.1 square meters. When multiplying these two values, you will find that the excavation volume to be 151.41 bank cubic meters. This simple volume calculation is best used for small excavation pits where the excavation depth changes linearly between the pit corners. For large excavation pits with non-uniform depths, you will need to break the excavation area into grid where a cut or fill depth volume value is obtained for each grid point. Large excavation pits exhibit nonlinear changes in depths over its area, so a simple depth formula cannot work here. You will use the same formula for calculating the excavation volume, but the average depth is calculated differently using the shown second formula here, which is a weighted average formula. Each grid point is given a weight depending on how many grid cells surrounding it. The weight of a corner grid point equals to 1 because it is in the border of only one grid cell. So the 4 corner grid points each has a weight of 1. The border grid points have a weight of 2 and the middle points have a weight of 4. The weighted average depth formula then sums up the multiplication of the depth and weight of each grid point and divide the product by the sum of all weights. An exercise in this volume calculation is shown in another video. For trench excavation, the volume is calculated as the cross-sectional area times the length of the trench. The trench cross-section depends on if you are leaving the soil shape at its natural slope or its angle of repose, which is case A. Or you will use a trench box for holding the soil side vertical and not caving in the trench, case B. We'll cover the angle of repose in one of the next slides. When calculating the trench quantities, you will always need to know if you will use a trench box or not. Typically, trenches less than 5 feet deep will not need a trench box per the requirements of the Occupational Safety and Health Administration, OSHA. Depending on the soil type, you can still end up with a vertical trench sites without even a trench box, like in the case of rock or clay. If the excavated soil is not loaded right away and hauled off-site, it will form soil spoils that will take the variable site space that needs to be calculated. The soil spoil can take the shape of a pile or a bank, depending on the excavation operation. For spoil piles, they form beside pit excavations and they take the shape of a 3D cone. So its volume is calculated using the shown formula as third of the base circular area multiplied by the height of the volume. The volume can be calculated from the excavated pit dimensions, but the base, or its diameter d, and the height h are now two unknowns in one formula. So we need another formula to relate both variables, which is done through the angle of repose of the soil, which should be known from the soil investigation report. Angle of repose is unique for each soil type, and it represents the natural stable slope of the soil pile. The shown table lists the R angles for different soil types. You can see that the more moist the soil is, the more angle of repose it will have. Also, you can see that dry sand has the lowest angle of repose, which I'm sure you struggle with when building sandcastles on the beach. So by going back to the volume formula, V equals 1/3 times the area times the height. The base area is circular with a value of pi d squared over 4. The height can now be related to d using the angle of repose and the triangle formed by d over 2 and h. By substituting h's formula into the v volume, you can calculate the diameter of the soil spoil pile by using the excavated volume v in loose units and the angle of repose. Soil banks usually form along a linear excavation operation, like the case in pipelines, continuous footings, and trenches. The volume calculation principles we discussed before still apply to the spoil bank, but we are now dealing with longitudinal dimension, the bank length. The spoil bank has two other dimensions, the spoil height, h, and width, e. As such, the volume equals the triangular cross-sectional area of the bank, half times b times h, multiplied by the bank length. The angle of repose relates the h and b variables, so we can adjust the volume calculation formula to make it a formula to calculate the pile bank width b based on the loose volume of the excavated soil and the excavation length and the angle of repose. We will switch gears now to volume calculations in mass excavation operations. The example shown drawings are for the mass earthwork example that we covered in part 1 of this lesson. If these hypothetical drawings were real with complete dimensions and more cross-section views, we can perform two quantity calculations that are fundamental to plan mass earthwork operations: end area calculations and earthwork calculations. End area calculation is used to calculate the area of a road cross-section at the end of a road segment. This calculation is performed for all cross-sections at the ends of the segments of the roadway. And then earthwork cut and fill volume calculations are performed, based on these end areas. End area calculations have been done in three main traditional ways. First, trapezoidal calculations involve splitting the cross-sectional area into a group of trapezoids that together follow the road cross-section shape. These trapezoids have the same width W, and the height values are calculated at each W interval as the difference between the final and existing grade. Then the total cross-sectional area will be calculated using the shown formula by multiplying the width interval W and the weighted sum of the heights. The weighted sum entails simple summation of all heights except for the two height values HO and HN at the two edges of the cross-section where the final and existing grade lines meet. These two edge points are also known as the toe of the slope. Only half of the heights at these points is included in the volume formula, as each of these edge heights are considered for only one trapezoidal shape. The shown example has 6 W intervals and 6 cross-sectional trapezoids. The slope, toe height, HO and H6 equal 0 in this example. The second and third method represent an old and a newer way to calculate the road excavation cross-section area. The second method utilizes a planimeter, which is a tool that you fix on one of its ends and use the other end to trace the shape you want to calculate its area. Planimeters are old tools for estimators when computer tools were not invented yet. The third calculation method utilizes computer-aided drafting (CAD) software tools to calculate the area of a shape. In AutoCAD, which is one of the available commercial CAD software products, you can use its command measure area to find the area of a regular shape. Now, there are more advanced computer tools that are specialized for heavy construction earthwork contractors that can calculate the quantities for structural and mass excavation and backfill. After the end areas are calculated for all roadway segments, the volume of each segment equals the average of its end areas, A1 and A2, times the length of segment L. The L value is very dependent on the geometry of the project, so it's determined based on the estimator judgment. The shown figure is an example of how the end area calculations are used to calculate the earthwork volumes. The figure organizes the calculations following the stations that mark the location of the cross-sections. They're calculated end areas, distance between two successive cross-sections, and earthwork volumes of each segment. The first end area is located at station 150, and has an end area of 360 square feet. The distance and the volume values for this station are skipped and left blank, as they require two end areas at two successive stations. The second station, 150 plus 50, has an end area of 3,700 square feet and away 50 feet from its preceding end area section. As such, the volume between the first and the second station equals 3759 cubic yards, as shown in the sample calculation here. The similar calculation is performed for each pair of successive station and end areas, and the total volume is calculated as 257,000 018 square feet by adding up the volumes of all the segments. Please notice that all end areas are for excavation cut, not backfill or fill, because all the end areas are positives. So the area calculations are sign sensitive. Also, you will notice that some segments had a length of 100 feet, like the third segment that is bounded by stations 151 and 152. Probably the project plans didn't have cross-sections details for the missing intermediate stations, or the geometry between the stations in this part of the road can be uniform over a longer segment length. Let's now see the impact of selected distance between the end area calculations. The first figure is the same as we saw before. The second figure is for the same project, but with longer segment length, 100 feet, for all the road segments that are resulted in less number of segments to add up their volumes. You can see the difference of the total volumes in both approaches, which accounts for about 2.5% difference. The first approach with shorter segment lengths is more accurate, as it captures better the variations of cross-sectional area over the roadway length. This is the end of this video, where you learned about volume calculations for structural and mass excavation volumes. Also, you learned about calculating the spatial dimensions of soil spoil, which is very critical in planning the layout and logistics of an excavation operation. I hope you enjoyed the video and have a great day.